All right, so here we go. Day number 3. So we're going to talk a little bit about ASM machines. Does anybody know basically what an ASM machine is? Or a finite state machine in general, an FSM? What's an FSM?
In a finite state machine, you kind of define different states that your system's going to be in, and then kind of you draw arrows between that are the different inputs or changes between the states.
Okay, so I have states and I have transitions. Is there anything else I have?
Inputs and outputs.
Okay. So the classic one would kind of look like this, where I've got, let's say for instance, state 0, and I've got arrows that talk about, where am I going to each, let's say state 1 is some transition, and back, right? So, now, the inputs go on the transitions. So I can say, for instance, if my input is a 1, I want it to flip. If it's a 0, I want it to stay. Right? So all state machines are going to have, finite state machines will have this basic construct in common. State name, inputs on the transitions. Right? Now, the difference comes on where do I put the outputs. There's 2 different locations. It could either be in the states or it could be on the transitions. Anybody know the name of the 2 types of machines? Mealy and Moore. Okay? Where does Mealy put its outputs?
Be on the transition.
On the transitions. Very good. The Mealys go here. How about the Moores?
In the bubble.
Inside my states. So the Moore outputs go here. What's the practical difference between these 2?
The same problem, more FSM usually have one more state.
So when you actually go to synthesize them, it's kind of cute. Moore, which is actually the person's name, M-O-O-R-E, right? So it's not the M-O-R-E. But it turns out they often do have more states, as in a larger number of them. So that's kind of a practical outlay. It's theoretically possible they could be the same size, but in general it's usually slightly bigger. Right? It can be up to twice as big. So Moores tend to have more. Mealy is a mealy little thing. Kind of a cute way to remember them. But that's not actually the biggest part of the difference.
You say more states or more outputs?
They often will have more states.
The more has to have memory associated with the state.
Okay? So the more has not just the memory associated, everybody has the memory associated with the state, but it has the output associated with the state, which is where the memory is, which means your outputs are synchronous. These are asynchronous. This is the big difference, right? So the question is, do you need your outputs to be synced to a clock? Technically, since this input does not have to come at the clock edge, the output changes the second the input does. So therefore, it's going to change asynchronously. Now, Mealy machines are slightly smaller and therefore slightly faster, but they're potentially asynchronous between domains, which can be dangerous. Moore machines are bigger, usually slightly bigger and slower, but they have safety on their side. Right? They're always synchronous, so everything's nice and clean in that sense. Technically speaking, I said it could be up to twice as big. But imagine every one of these Mealy outputs was different, all different from each other, nothing in common on any of them. Then theoretically, in this case, I would need twice as many more states. Because I would need a more state to handle that output, and I'd need a more state to handle this output. So I'd need 2 for this one. I'd have to split this one into S0 that's staying and S0 that's going. So I could handle the 2 different outputs and just clock them. Right? And because I therefore have those, it's going to be slower on the transitions. Same thing down here. So if you have lots of transitions going out, you could theoretically, if they're all very different, because you can have a large number of outputs, I would have to, when I go to more, I could have to add lots of different states to handle each unique output. So they can get really big really fast. All right, does it make sense where those are coming in? All right, now those are kind of the classic ones for finite state machines. And you can take these and kind of convert them. The typical way we do is we'll take these and then we'll kind of write code blocks from them or switch them to get a state transition diagram and then try to convert them. Now, these are okay. There's nothing wrong with them, but there's a slightly nicer way to do these. So if you've ever written code from like way back, they have these lovely things called flowcharts. Right? And flowcharts basically gave you a nice graphical way of organizing things into blocks and units and everything like that. And code was very easy to write directly from a flowchart. You could kind of just look at them and write your code. It would be much harder to sit here and just look at this and write code. So this is an ASM chart, algorithmic state machine. All it really is, right? And we'll have another one, ASMD, which is algorithmic state machine with data, right? But the big thing is not as much where the name is. Just think of it as a flow chart that has states. Right? So instead of having these round states, we're now going to have square boxes. That's our state. Right? So it will have a state name, which is usually listed right up here in the upper left, typically just outside into the top. And then inside this block, I can put whatever I want. I'm going to assume the ASMD version, because even though the book does 2 different chapters for them, the difference practically is really small. Technically, an ASM chart just has these and the outputs and everything basically the same here. How does it handle inputs? How does it handle outputs? But we might also want to have some explicit calculations, and where do those calculations occur? The ASMD allows you to have variables in it, and you tell them how you process them and where you process them. So I'm just going to assume the ASMD because that's really more what you're going to do. So I can inside here list whatever processing I need to have happen, right? A calculation occurs, whatever else. I just write the equation. Right? So whatever needs to happen inside that state, I place it here. If there's an output that needs to happen, I place it inside there. Make sense? Okay. Now this state, I have to be able to decide where my transitions are. So this is the classic, what's called a decision block. Looks like a diamond. Right? And inside here you list some condition which is typically evaluated to true or false. Right? So for instance, if I was making this state to be S0, and I wanted to make a more machine, I would put my more output here, it's just inside the state. My condition here would be whatever my input is. And if it's a 0, I would come back around. Right? And if it was a 1, I would head to my next state, which was S1. Make sense? So that's where the more outputs would go. Where would the mealy outputs go? Well, I have to do it between these two, so, but I don't want a whole state here. So I need to show something that you're going to do something, but it's not its own state. So we round the corners. If you round the corners off, it means it's a conditional block. It's not its own state. It happens in whatever state is directly upstream from it. So it just means this processing happens after the input. Right? This is where the mealy output on this 1 goes. Right? 1's mealy output. 0's mealy output would go right in here. Whatever its mealy output was for 0. Does that make sense? All right. So inside S1, right, I would have its more output, and then I would go down the same thing. I would have an input block. Now, but notice I'm running out of room here. I'd still like to be able to fit it. Part of the problem is this is, while it's kind of unique, easy to notice as a diamond, it's really space inefficient. I don't have enough room to draw a decent sized diamond down here. So what we're going to do, we're going to truncate our diamonds. So if you ever see this shape, it's still one of those decision questions that's going on. And this is actually where they got it. It just removed all that kind of wasted space on the diamond that allowed me to then fit in whatever else you want. Make sense? And so in this particular case, again, I'm checking on the input. And if it was a 0, you have some mealy output, potentially. And I come back around. And if not, I have a different set of mealy output, whatever that is. And then I come back around to this state. So now I have an identical one now inside a flowchart or ASM. And I could specify code that I want to run in each of these areas. Now here's the nice thing why I say this one is so cool, right? If you take this, you can directly see, like, what if I want to do multiple different input checks, right? I would just have the different values along here, but you don't necessarily know the priority to them, right? So if I wanted to check on an input, you know, is it 1, 1, right? 1, 1 or 1, 0, and, you know, maybe I wanted 0, 1 on some other arrow, and, right? Maybe 0, 0 on something else. I could have different ones that carry in. How do you know the priority of where they should be handled? Do you want a routing network? Do you want some large multiplexer? Right? There is some ambiguity in what you build. If you don't give me anything else, I'm just going to go, well, it's flat, so I'm just going to put in a multiplexer. Now I can do that over here, right? If I just take my decision, I can specify whatever the input is multivariable, and I can cut out and I can go here's 0, 0, here's 0, 1, so on and so forth. So I can just put this kind of like little Christmas tree hanging thing off here and hang whatever I want off of it. And I just, on each of the downward arrows off of it, I can put your individual strings. That would specify a nice simple multiplexer area or a case statement. It's very easy to tell a case statement inside my spot. But on this one, I can assume that's probably a case statement, but what if I wanted a nested if statement? I wanted priority routing, not just routing, right? This is going to route, but it's not going to give me any priority sequence to it. there are times when you want priority routing, right? Certain things have higher precedence in what's going on. That's what happens inside your kind of standard mux to a mux situation, right? So imagine okay? There's a priority routing. This one has priority over that one. This one only works if that one lets it. This is my highest priority. Well, sometimes you have a high priority signal and you want that really stupid low latency path, right? Because it's your most common case, it's really important, whatever it is, you need that priority route through the system. Right? When you build a really big thing, they're all the same priority, but it can be slower to handle those type of larger systems. So there are times when I want that type of a priority. That make sense? How do I specify that here?
You have to write things.
You have to give me a note. There's actually no way you can tell me, because you don't have memory in between here, so you can't separate a state out. It's impossible in these diagrams to tell the difference between this condition and this condition. But I can cascade input checks. You do one box flow into another box and generate a priority. Or I can do a tree off it and show you a case statement. So ASMs can distinguish them. So this is one of those areas. There's a bunch of spots like this, but this is one of those really easy, obvious areas that you can see that this one directly tells me the code and the hardware I'm going to build. This one gives you options. There are times when options are nice, but there are times when a design intent is really important. Right? So we often would rather go to here because we can specify our design intent. So that's why we're going to prefer over on this side. Now, in an initial course, when you're dealing with, calculating digital logic and things like that, we normally have you do the other ones. And the reason is it gives you lots of options, so it makes a much easier state transition diagram, so that you can now try some of these different things, and you can also run into problems, and you can check all kinds of different things. So there is a certain amount of flexibility that you at some point in your career have to handle, right? But when you eventually go out to get a job at a company, you may be the one who specifies this in, but you might not be the one who builds it, right? And you don't want to specify something that's right, you've got it worked out in your head, and it must be done a particular way, including priority routings and everything else in order to be able to function. You don't necessarily want that later person misunderstanding and implementing the wrong thing. And if they do, you certainly want to be able to say, well, you misunderstood. You did not follow what the diagram said. That's why there's a problem. Okay? So being able to specify exactly is an important thing. So there are places for both. So I'm not saying no, but I'm saying for us, we're going to stick with this side. Make sense? Okay, let's turn this into code. What would we do?
You have to initialize it. That's your first case.
Okay, so we're going to have to initialize. What am I initializing?
That's state variable.
Okay, so now I actually have to have variables. Right? So I'm going to therefore have something that's going to have to not just, for my program that I'm going to write in Verilog, but it actually has to generate memory that has to actually exist. So I'm going to have state. Right? That state is going to imply flip-flops that have to be initialized. All right? What else do I have?
Some local parameter, parameter to be used in compile time to store the encoding of state.
Okay, so I'm gonna have some state encoding. As long as we mention state encoding now, what encoding schemes do I have? Okay, one hot. Right? Binary would be another one, right? There's tons of them that are out there. You know, so these are probably the two most common. I am happy that gray code was mentioned too. We'll talk about what each one does. But let's say these two are our two most common. What's the advantage of binary?
It's easy and
Okay, people, it's kind of the natural one we think of. Anything else with it? It's really compact. If you're trying to separate a number of possible states with as few bits as possible, it takes the fewest number of bits to enumerate the largest number of states. In particular, if I have n bits, how many states can I enumerate? 2 to the n. That's an awful lot of states. Yeah.
In fact, speaking of compact, I've been thinking about if Huffman encode could be used in state
So
encode.
you can, and there's actually, you can use cyclical coding too. There's a couple other ones that actually make sense to do certain amounts of efficiency. Just remember, the better you pack the data, the better you have packed the data. You have to unpack it to use it. Right? So this is what we call time-space trade-off. Right? I'm saving memory, which is often actually fairly crucial on large projects. Memory is actually usually more crucial than time complexity, because you just run out of space quicker than time. I'm getting a fairly efficient one here, but that means to actually diagnose them, I've got to explicitly check each separate code. Right? So this one tends to be very space efficient, time inefficient.
What would be the opposite?
The opposite would be space inefficient and time efficient. That's what one hot is. For this one, so this one is really good if you want, you know, a fast solution that goes on. I assign 1 bit for every state. You have n states, you need n bits. Right? So that's the same, you know, n bits, n states. This one has 2 to the n states. For binary. The way one hot works, you know binary is your normal counting thing. The way one hot works is the first state, 0, 0, 0, let's say just it's 4, that's state 1, state 2, state 3, state 4, that's all you get. Right? Those are the only codes you use. Now, the reason why this one is nice, you can actually even see why it's called one hot. Right? Because 0 usually means ground, 1 means power. So only 1 bit is hot at any given time. The nice part is it's really easy to decode. Like if you wanted to say if something was going to happen in state 2, all I'd have to do is take that bit and just pull it out. Whereas if you wanted to check state 2 over here, you'd have to write a logic function to decode state 2 into a signal. Make sense? It's not too bad at this part, right? State 2 is just going to be, right, that. There's your decoder. Right, looks for a 1 and a 0. But as it grows, that gate is going to get uglier and uglier. Right? And fan in will start affecting you, and you'll have to go to multiple stages, which increases your latency. So this gets slow. All right. So this is the idea with 1 hot. Again, space inefficient, time very efficient. What's gray code used for?
Is gray code the one where there's only like one change between two?
Exactly. Between 2 consecutive numbers, only 1 bit flips. It's highly compressed, so it's got the advantages and disadvantages of binary. And it has the added lovely advantage of almost nobody can read it. Right? Because they confuse it, because it looks just like binary and people misread it. Because when you see it right, you get 0, 0, 0, 1, 1, 1, 1, 0. That's your sequence. This is the same one your Carnot map uses. So if you ever get the things flipped on a Carnot map when you're doing them, it's because it uses gray code. Because it wants only one thing transitioning on any edge. Why would I ever want to do this?
Synchronous,
What?
synchronous. Cross clock domain.
Across clock domain. So this is particularly, let's imagine I have an input device. So imagine I was dealing with, like, let's say I wanted to run a drill, right? Or I wanted to run any other type of, let's say, a rotary machine of some type. I could put on the shaft of whatever device it is that I'm trying to run that's rotating at some high speed. I could put like an LED that's shining, and I could have, you know, a little wall between it, and I could have a diode to read back out, right? So the light bounces and comes back, and I could read. And then I could, on here, I could paint a series of symbols, right? And I could reproduce this reader circuit over and over again to read consecutive bits, right? I just put the lines that come through, and I either put them painted or not painted, right? Absorb the signal, don't absorb the signal. So now I can read a code. Now I could theoretically put any code I want, but if your codes change too quickly, it's very easy, if you're not reading at the right rate, to get an error. What would be really nice is for my encoders to only have to deal with 1 bit flip at a time. Because then they're really close to where I was before, I could do that very quickly. Right? So this is going from an analog domain to a digital domain, that conversion. Anytime you cross a time domain, gray code has a place. Because only 1 bit is flipping, that means there's much less problems that can happen. And in particular, a really important one happens on these ones. So if you've ever looked at these, they'll do a similar type of thing where you can actually put, as a real simple thing, if you've ever done a weather vane, you can have a metal vane. You can hook that metal vane to ground, for instance, you know, or some low voltage signal. And then on this, you can put tape, which is an insulator, and then you just put a spring resting against it. And as it rotates, if there's no tape, you get connection. If there's tape, you get a disconnect. And so it'll turn it into a high-low signal that goes on to it. So it makes a nice, simple little device for reading and encoding things out. Same idea with doing this. That's how, if you've ever seen robots with wheels, they paint those little disk charts on them. That's all they're doing. It's gray code. Because it's really efficient, because only 1 bit changes, so it's very easy to find errors, very high efficiency, things of that sort. So really nice across time domains. That's where gray code comes in. All right. Does it make sense? Okay. So we'll play with these. These are kind of some standard ones that go in. I've got to figure out an encoding for them. And we'll deal with that in a second. Anybody know, how do I often handle encodings inside Verilog? So type def is what we get in system Verilog.
Yes.
So that's a nice thing, we get an enumerated type, right? What we used to have to do is declare local parameters, right? And so we do a local param, and then we would just say whatever, S0, and we would set it to be equal to whatever, right? And we could specify that it was, a reg of whatever size. But we could basically set these S0 and give it a number, right? And that would allow me to specify the encodings. If I don't specify the encodings, what happens? Xilinx gets to pick. Anybody know what Xilinx picks by default? It's one hop. Right? And it picks one hop because it is actually the easiest to design on. It makes its job the easiest, so if you say nothing else, it's going to do that. That being said, it's probably a good idea for you to know what you should get. So it's worth understanding. But you would do a local parameter. Whereas now we're going to create our own types. That's an enum type. So that's actually allowed to us now, where we can actually create these enumerated types. And right, so it gives us in addition to type def, it gives us enum, right? And that enumerated type, you can actually specify, for instance, S0, S1 as my enumerated type, and whatever I want to call it, the name of this. The key thing that's happening with this one is this is still not specified what the encoding bits are. So it'll allow them to be picked. But it does actually set them as its own type. We can also do an enum where we have, say for instance, logic, and I can say, whatever. Let's say I just specified one bit here. So I could say logic and then S0 equals, and I could say 1 bit binary 0, and S1 equals 1 bit binary 1. So I could also do this type of situation that was in. Right? And that allows, right? Enum allows me to access an enumerated type. If you specify logic, I can also specify a certain number of bits. In this case, I only needed 1 bit. Right? So I didn't give it anything else. But I could have said, if I would want to go the other way to do a 1 hot, I would have done 1:0. And then I would have 0, 1, and 1, 0, and there would have been a 2 there. Make sense? So I can do type defs, which is kind of a nice feature. And now I can declare things of that particular type. So I would have to declare, right, these values to be of that type, and the state variables and the next states would also have to be that same type, because I'm going to match the types when they're going across. Right? This is a worthwhile thing to mention in here. One of the unique things about logic, right? We said we're going to use logic instead of wire or reg. And I kind of hemmed a little, just like, there's always a little caveats on here. Logic presupposes 0 and 1 is what you're designing for. Right? X and Z are allowed, but they are going to flag you with a problem, because you can't synthesize those. Right? So logic is actually not only just a simpler way of not having to pick wire and reg, it also specifies a design intent, that I want all of my bits to eventually end up as 0s and 1s, because that's what's synthesizable within my system. If you want to be able to synthesize not 0 or 1, you have to do a different thing like a wire to do them, because this will not allow you to synthesize non-0, 1. Internal to an FPGA, is it possible to synthesize something other than a 0 or 1? Correct. No, it's not. You cannot, inside an FPGA, you cannot synthesize anything else. Hence why we really like logic. Right? Because if you attempt to, if you get an X, it knows it's a short circuit. right? If you get a Z, it knows it's an open circuit. These are not good values. Is it possible in an FPGA anywhere to get a non-zero one? Yes. That's obviously not internal. So where's the only spot remaining? I/O. Right? Your I/O ports to save space, they don't make input ports and output ports. They make I/O ports. All I/O ports look like this. So this is internal to the system, and this is external. Right? So this is your output, this is your input, and this is output enable. So what is this strange beast? Tri-state gate. Right? What happens if I don't assert output enable? You're disconnected, which means it's a Z. So the only spot you can synthesize something else, you can only synthesize a Z, and only on an I/O, by setting the output to not be it. But if you still intend it as an output, you technically still get a Z, because you're not using this. There's no draw. Why would I ever want to synthesize Z? Where do I use Z? Bus. Right? If I want to hook two chips together, I can get a protocol that says who talks when. At the other times when you're not talking, you have to cut yourself off the line. Otherwise, if I've got two chips trying to talk on the same thing at the same time, right? One writes a 0, one writes a 1. What happens? Short. Right? It doesn't work. But if they're both writing Z and only one's allowed to talk at a time, one's writing, it controls the bus. Why do I want buses?
So that we can, like, we'll use it for, like, if you have multiple dies. maybe you can-
Could I technically replace a bus by just more wires? Yeah, of course I could. Right? Does it have any advantage? Yeah, there's no contention. You can never have contention, so you got a stupid amount of bandwidth. What's the disadvantage? Yeah. It's just, eventually you end up with too many wires. Right? Wires take up space. Space is the thing we're actually really short on. This is why I say time complexity is nothing compared to space complexity. Space complexity is far worse. Right? So we really don't like that one. So buses is one of our solutions. Plus remember, all of your calculations are being done inside a cube, right? You build all your circuits inside there. So the complexity of circuit available to you, you can stack them and layer them. If I have n on a side, the available computation is n cubed inside that space, component-wise. What's my allowable data transfer? It has to go through the surface, which is proportional to n squared. So the bigger a chip you can build, the more powerful you get things. Your data is not growing at the same complexity that your computation is. You're in deep trouble. So the best thing you can do, since your trouble is transfer, is to reuse as much as possible. That's what a bus lets me do. Because I'm fundamentally limited by the universe. Right? Make sense? Cool. All right. So that's kind of where this one goes and where you should think about how your enumerations should go. So you really do want this logic. Right? Okay. So that basically covers how I can specify my encodings. We good? The book has a very nice section talking on this too. But I want you to get the ideas and understand why. So, all right, so that's my encodings. What else do I need? I've got my states, I've specified whatever encoding I want, whether it's one hot or binary or whatever. What else do I need?
State transition
I
and
need the transitions,
output logic.
right? So we sometimes call this the next state. So anytime you deal with these areas, there's really two parts. There's the state and the next state. Dead minimums, you can't get away from this. We do not want you to combine them. There are some companies, and I've seen some people argue passionately why you should do all of these type of things in one big thing, right? And they are dead wrong. And here is why they are dead wrong. Because if you put them both in the same thing, next state is what type of logic? Combinational. What are you dealing with in your state? Synchronous. So on this one, I want to make sure, remember our danger? This one needed non-blocking commands, and it needs to be edge triggered. This one needs to be triggered on any event, i.e. asynchronous, constantly going, and it needs blocking. I can't mix the two types. So if you mush them together into one thing, one or the other is going to have a high likelihood of generating an unexpected error. If you build them separate, using their own proper formats, you have now avoided an error. Right? So we want to split it into two because of what we talked about last time. We want to do this with an always underscore flip-flop, and this one with an always underscore column. Make sense? And we'll do what's inside the states here, and the state is just going to be a simple flip-flop. Make sense? Okay. So we're going to do that now. The state part is really trivial. I'm just going to put positive clock. You can obviously add reset too if you want. But just for time efficiency, this is where I'm going to leave it at. Right? So, right, at my positive edge of the clock, I'm going to, right, that's the only thing that's happening here. So I can now say that my state, so let's assume I defined state to be of whatever that enumerated type was. Right? So I can just say state gets the value of next state. Right? Simple enough? What would happen if I put a reset in?
You have to know what you want to initially reset to.
Yeah, so I would have to say, if not reset here, else, and then I'd have to have my condition for whatever reset is. Right? So maybe like state gets state 0 or something. Right? But that's the only thing you would be adding into it. State is always stupidly easy. It always looks something like this, because all you want is the flip-flop to hold it. Okay. The next one, the transition, always underscore comb. I don't need anything else. It'll automatically do the @ star for me, so just leave it alone. Anything else is just going to add confusion. Now, I've got different states. In each of my different states, where I'm currently at, I'm going to want to do something slightly different. You could potentially up here have a, what we could call base cases, or, if nothing else happens, this is where it goes. This is an optional thing. So remember we said that you want to make sure that you handle every possible situation that could be out there? Well, one way is to make sure the case statement includes everything that's out there. The other way is to just put a base case that initializes next state and whatever else matters, the outputs, so no latches can result. And we just put them inside here, right, as what the base condition is. It's an option, right? So I'm just going to put that as a block here just to remind you, you always have that capability. Right? Then we've got a case statement. What is my case statement going to operate off of? Right? Yeah, whatever my current state is. And at S0, what do I need to do? I've got whatever my MO, whatever was in here, right? I need to put that here. That always happens, right? If this state occurs, that's the first thing that occurs. That's what's so nice about these. You can actually just walk through these sequentially, right? You start here and you go, first thing I see. You walk through, if there's multiple things in here, just put them all in, right? And I walk through this along this, and then what's the next thing I see? It's a decision. How many possible outputs? 2, so what is it? Right? Possibly if I'm assigning a value, or I could just call it in if. And what's the thing I'm checking? What is? Now I could just say input equals 0, input equals 1, but since there's 2 options here and there's 0, 1, they'll also map to true, false. So I can also just say if input. That means the true part goes here. That means I'm coming down here. So this is the mealy of 1 versus the mealy of 0, just to distinguish them. And that was the more, right? So I would have whatever's inside the block, right? I'm now taking the 1 route. I go, oh, I see this. Next thing's the next state, so I can stop. I just put the mealy of 1 there. And that's all you do. Else, if it didn't go down this route, what did it do? It went up that route. All right? I am leaving a little bit of room because there's something else that happens there. Now, that gives me my mealies. What's the other thing that happens there and theoretically here? That's at my next state. And what is my next state for 1? And then you obviously have to put a begin end. Right. And the same thing here, right? You'll need a begin, end, and a next state. Right. Technically, in this case, next state gets the value of S0 still. Make sense? So help me out. We just did S0. What do I have to do for S1? And obviously I have my begin, and then what do I do? I do my more output. You start where the state name is, and you walk through. More output. Whatever else was in here, you do all that. And then what do I see? If my input is true, what happens? I would do this mealy, and my next state would be S0. Otherwise, else, I do that mealy, and my next state is S1 again. Done. See how nice and easy it is to go from this to code? The other nice thing is if you write your code this way, it's really easy to walk through here, right? And you can just take a look, oh, initial conditions. This is what's set in the state block. Here's my first decision block. Here's what's in the conditional block afterwards. Here's my other line. Here's what's in its conditional block. You can walk through your code and you can generate the ASM trivially if you write the block code nicely. Right? That's really nice for documentation purposes. Right? So do we see the nice advantage of these? So this is the way I really want you to kind of think about them, particularly for FPGAs. Because this sequence, using the enumerated types, breaking them into an ASM chart, and then you can convert them. And realize we did that generically. You could replace as many lines of code as you need on those. You can now build whatever you want. And, actually I should have done these. Yeah, everybody should have flagged me on that. I shouldn't do, that should be a straight. We want the instantaneous, i.e. the blockings. There and there. Because remember, we want blockings inside the columns. Yeah.
So, design support register initialization statement, like register state equals binary 0, just code like this. It will be initialized to 0, this register. But what kind of circuits is it actually synthesized?
So, let me give, let's say R1 somehow becomes, whatever that register is. If you do something that does this type of thing somewhere inside a block,
No, just blocking assignment. Yeah.
inside a combinational,
No, just one line, like register R1 equals 0.
oh,
That support this kind of initialization.
it does. You gotta see whether or not that register becomes a flip-flop or not.
What?
Because remember, regs do not necessarily build memory,
Yeah,
right?
you can use it in sequential logic.
It can become, this could become a wire in a combinational circuit, or this could become, right, a flip-flop that's in there, right?
Yeah, how could like FPGA handle this initialization?
So it's,
That
it has to be different depending on what it synthesizes, right? So for instance, if it is, and this is not specific, when exactly does that happen? So this is not a good synthesizable format. This is good for simulation, but it's not particularly good for actually doing synthesis. A better way to actually do this so you know what you're gonna get is don't do that, right? And then create a global variable, let's say like run, right? Run is set to 1 when the system is running. It's set to 0 during boot or things of that sort, right? So what you can then do is if you have a run state that's going on, and I can then say, looking for at the pos edge of whatever that run variable is, right? Or I could do it during when run equals 0, would be an alternate way of doing it, right? But at that pos edge of run, I could then have R1 get assigned 0. Which now I know exactly what that looks like, right? Because inside this one, it's a system that's waiting for that. I could either implement that as a clear, or I could pipe a 0 into it when it's clocked input, right? So this type of a system, I could put that inside, like an always or something like that. When I do my transition to the run state, clear that register, right? Now, the danger that comes to this is if R1 is declared somewhere else, and I've got 2 of these that are always writing to it, that can create some areas. So I have to disable that other one at the same time to prevent them. Your other alternative is put this code here, and this is the nicest of all forms, in addition to my pause edge reset. Right? I could put all of them in, and I could check to see if, you know, I'm at my run state, or if my last state was 0, right? So I could look, was it a pause edge of run? Was it a pause edge of reset next? Was it a pause edge or of the clock? And just handle each one, and then do this assignment inside the flip-flop, right? Which I could then just do by the asynchronous clear, and it becomes clear. So this would be my preference, would be to build in the logic internal to the system. And the reason is that I would like to modify whatever my thing is, whether it's R1 or state or whatever. I'd like to only let a variable be on the left-hand side of the equation in one always. One and only one. It's not illegal Verilog to do it in multiple, but it's potentially error prone. The error comes in, what if both write at the same time? Right? That's the danger. Now I can put interlocks to try to prevent it, but what if I go across clock domains? One's in one clock domain, one's in the other. There could be a time shift between them. So they could end up.
I understand. Let's say we have a shift register, 4-bit. I could use that kind of initialization statement to initialize the shift register as any type of bit pattern as I want, like 1010. Once the clock enable is enabled, it shifts 1 bit from input and output 1 bit from the top bit. So what kind of circuits is this initialization statement synthesized?
If I put the equal 0,
Yeah,
there's no guarantee it can, and it probably won't synthesize anything. So now you have to say, what is your tool going to infer? Technically, that tool should not infer something, it should flag you.
yeah, but it can't infer.
Yeah, they will sometimes infer, right? I can write something to infer, right? It's possible for me to say, right, any of our FPGAs do have an initial boot period where they load things in. So they could decide, infer, load from my external ROM.
Oh, you mean the same way when I wanted to?
They can make that
initialize RAM?
inference. They could say, infer a clear at the start. Right? The problem is, you're now dependent on what does the tool say. You don't know what it's going to do. There's no standard that says what it should do. Since there's no standard, you don't know what happens. And you don't know when you go to a new system, what is it going to do. Right? So it will probably work most of the time, but since you don't know how it's working, you could end up with some weird behavior. Right? I generally don't like that. So I like to be explicit. Right? Can you do it? Would it probably work? You'd probably be okay most of the time. If I was building a kid's toy, who cares? You know, maybe there's something a little funny right at the start. People just, parents just go, oh, the battery must be getting low, because they know nothing else, and they just move on, right? And so, but then the toy starts working fine, and away we go, right? If that's at startup and it's on somebody's pacemaker, might not be such a good situation, right? So now you have to look at how critical the design is. The more critical the design, the more I'm going to sweat what does it really build, right? If I know in advance it's going into something low criticality, you're right. I'll take whatever it builds, because who cares? Now it's speed. How fast I turn this one out, the more I turn out, the more money my company makes, the safer my job is, right? Nobody's going to care. Right? When it becomes critical, biomedical systems, things like that, I care. If I don't know, I assume the worst. So, in general, I would assume they would generically, if you're saying it to 0, most likely one for a clear, an asynchronous clear at start. And there is typically a startup flag, like a run flag. Right? And that run flag is probably going to do an asynchronous clear. So that is the most likely circuit that it's going to develop, is it's going to, with that, transition to run from boot time flag, that it will set that to 0 just before it starts running, because then that happens just before your program takes over. So it does all the rest of its booting stuff, and at the last possible instant it goes. Because if it did it earlier, somebody else might have messed with it. Right? And you want it to happen a little bit later because you want all the transient voltages to work out. Right? So that's, but if I specifically have those type of run flags and stuff available to me, it's much better to use it. Right? Then there's no question. Because the other way, it could just load a 0 in from its default stored memory, which is also perfectly acceptable from what you specified. Right? Multiple choices, how much does it matter if you know which? The only danger with the loading from memory is you could load it from memory and some later thing could override it. You don't know the sequence. Good? Okay. If we feel comfortable with these, let's talk a little bit just about how we handle timings and everything. Has everybody at some point made the 7-segment displays on any board you've used become readable? Right? So that's kind of one of those underlying things, right? This is a timing circuit. So that you're going to have to do, that's kind of the lab area for the next week. If you look on Canvas, it'll give you the problem number. I think it's like 464 or something like that. But it tells you specifically in the Canvas problem which one it is. And it's that timer I was mentioning, right? You have 3 buttons. The first button tells it, go back to the start state. And then you've got to go, and then it'll count some random time interval, and then it'll turn a light on, and then you, as fast as you can, try to hit the stop button. That's the basic idea of the problem. So think about how this problem is going to flow in terms of these. So what are our potential states we might have to deal with? I've got that first button I push that gets me into the ready state, right? That makes sense? So I have to have some type of a ready state that's available to me. Right? You push a button and it gets ready to go. Right? But it's not actually on its own going to do anything. It's just going to sit here. Right? And it's going to sit here until what happens? You have to push that second button. You have to push a start button. So this one in general is going to have a choice here to make. Right, so this is the start button. If you didn't press the start button, if you did press the start button. And here you'll just initialize everything. Right? We'll set it back to your initial conditions. Right? That's kind of my ready state. Make sense? What would I have to do with the start state? This was the start button. This is my start state.
Did you say you were waiting? You hit start and it waits a minute and then
Wait some time,
waits some time.
right?
Maybe they're
So
very-
I forget the exact number they specified. I think it was like 2 to 10 seconds or something like that, right? It waits some random number of seconds. Why would it wait a random number of seconds?
That way it's not the same every time, so the person can't predict it.
Yeah, you can't get used to timing the second you push the first button, kind of, so you're cheating, so you don't have to wait for the light. Right? So it forces you to have to wait for the light because it gives you a random and you don't know what. So how am I gonna handle that random weight?
Is there a random function?
There is inside of System Verilog. System Verilog will give us a rand. Okay? So, now I could set that number in advance by putting rand here so it's ready to go. I could do it right at the start. Right? So somewhere along there you have to do it. Right?
How does it implement that when you synthesize it?
So there are, right, pre-done circuits that are random number generator circuits. How you build them, the most common ones are what are called pseudo-random numbers that are out there, and this depends on what libraries they give you inside Xilinx for synthesizing them. The typical pseudo-random number generator takes a number of states that are in, and they've got taps off of them. And they do a calculation based off the value coming out of the, so they might have like a series of bits, right, that are going through, and they'll take, for instance, the taps between these states, and maybe I take this one, and this one, and this one, and I XOR them all together, right, and I use that one to feed back in, right? That's going on. And then here's your output bits, and you ask for a certain number of bits. Right, and so depending on where you set where these tap locations are and things like that, this is kind of a classic, simple pseudo-random number generator. If you pick the right spots, you almost always want XOR. It turns out you don't need overly complicated ones. You can actually get pretty good random numbers. Right? Not the greatest in the universe, but they're pretty decent. So, anyway, you do want a few at the end here because a random number at the end doesn't let people know when you grabbed it. The other thing you can do is also just grab it in the middle spot for your output. So people don't know exactly where you grabbed from. So they couldn't just infer what some of the numbers coming in were. Right. But that allows you to get a fairly decent sequence of zeros and ones. You pull out as many as you want. So, but there's lots of pre-done hardware that do these type of activities. If you want to get to true random, there's only a few ways you could do it. Like the best way is actually have a small Geiger counter. Right? And the number of radioactive decays that hit you in a particular time interval is your number. There's no way you can predict that. So those are some common ways that people will do. There are actually some true external systems that you plug in for random number generators that use that Geiger counter system. Anyway, you can even buy some of the Geiger counters from SparkFun. But so anyway, you can get a random number and it can synthesize those. Fairly simple, just registers and tabs. Right. What am I going to have to do once I have a number, right, from the random generation? What do I have to do?
You have to wait that long, so there'll be a delay, and then turn on that delay.
Right, which means I have to somewhere along the line here build a counter, right? And it's going to have to count up, and when it counts up to whatever that delay is, that's when I exit. Right? So the second I press this button, I have to start that counter, whatever that counter is. And then I'm going to have to check to see whether or not that counter is equal to my random number, whatever that random number was you generated. That make sense? So you start a counter, the counter is going to output a number.
What does it say in
This
the one below it?
does the counter
Oh, okay. Counter equals equal.
does it equal the random number?
Oh.
I do admit my handwriting is not beautiful. The point is, right, I'm just kind of walking you, all of you can kind of come up with these yourselves. What I'm trying to let you know, this is the basic thought process you can walk through, and this is why these work nicely. right? You just say, hey, I've got to do it until it hits that random number, whatever I generated was, right? And the second I do, now I have to hit, this was start 0, this is now start 1, because it's still part of that start state. But this is where I have to turn the light on, right? And now I have to start the counter again. Right, because now I'm going to count how fast are you. I can use the same counter if I want, so I don't have to build 2 of them. I just start the counter all over again, and then all I now have to check to see is, did you push the button? Right? Did you press stop? No? And it keeps on going. Keep the line on and go. If you did, then I'm going to have to stop the counter and display the time. Now I'm at my stop state, and I have to stop the counter and show your time. And what's the only way to get out of this state? Yeah, that kind of reset, get me back to, right, remember we had 3 buttons, right? So whatever you want to call that, the reset button, or however you want to do it. Did I press the reset button? Yes. You come back up. No. Keep showing it. See how easy that is to do? This is kind of the nice thing about these ASM charts, is with a very brief human level description, I can walk through and say what needs to happen. You could do the same thing with a light, right? Show the, if it's your turn, put the green light on, wait a certain, start the counter, wait a certain number of seconds, turn the amber light on, wait a certain number of seconds, turn the red light on, right? I could walk through all of those nice states. I could make a stop sign, I could do anything off of them. Make sense? Okay, so try to walk through this, and you can see, right, we kind of glossed over some of the step areas here, but you got a basic outline, which is what I wanted. So start looking at that and see if you can implement that one. It's due technically next week, beginning, but should give you time to synthesize it and get it working. All right.